Welcome back to week 10 of SC0X. And we're going to do something a little different this time because in the previous weeks we've gone through optimization, we did a little bit of regression, we did simulation, and we talked about some statistical tests. What I'm going to do now is introduce the idea of a process because this is key to supply chain management. And I want to lay the mathematical groundwork before we go into some of the other implications of it in later courses. So let's think about a process. And a process simply has inputs, so things that get put in, and somehow those are turned into outputs. And in between this, there is some process, some transformational process that does the transformation. So think of manufacturing. You get raw materials, you do something to it, you stamp it, you drill it, whatever, and you have an output, a finished product. Supply chains work the same way. So you can think of it, your inputs could be orders to a system, and you get shipments out, for example. And we'll use this process, this input-output model, when we talk about a lot of things in future courses, such as how do I measure the efficiency of a process, which is simply the amount of outputs divided by the amount of inputs it takes, or how much of the inputs am I using, my utilization, or how effective is my process by looking at the quality of the outputs. So this is a standard framework we'll be using a lot as we go forward. We're going to approach it in this class in two different ways. First, we're going to talk about queuing theory, which is a very rigorous mathematical approach to understanding and characterizing the behavior of queues, and that's just British for a line, waiting. And then we'll talk about discrete event simulation. So we did some simulation last time. This is a special kind of simulation. It's very much related, but I want to explain why we might do it this way. So queuing theory. Queuing theory starts with the same process. I have inputs, somehow I process them, and I have an output. And so we can think of different ways that we measure this. I can measure this in throughput, which we're going to call TH, and this is simply the number of items that I can process in a unit of time, right? Widgets per hour, widgets per day, something like that. Then we have something called WIP, or work in process, and that's simply the number of items. That's the number of items that are in the process at any one time, on average. Then we look at cycle time, and cycle time is simply going to be, the units are going to be time. That's how long does it take when I enter the system to when I leave. So these are three ways you can measure any simple system. How the throughput, the processing through, how many go through in a unit of time, how many are in the system at any one time on average, and on average, how long does it take for an individual item to go through. The reason why we measure these is because they're key metrics that we want to find out. These are the key things we would want to find out if we're designing any kind of system. And what's nice is there's something called Little's Law that ties these all together. And it's simply that the WIP is equal to the throughput times the cycle time. And if you look at the units, they all cancel out. But what is this saying? It's a wonderful little rule. It's more of a unit conversion than really a law. But what it lets you do is observe a system and to be able to calculate the missing metric. So if you go to a line, you can usually see what the WIP is. That's the number of people waiting in a line. You can look at the throughput by just looking for a while and see how many people go through in the course of an hour. That's my throughput, items per time. The thing that's really hard to get is this cycle time. And by having these two, by observing these, you can calculate cycle time, or vice versa. It's a very well-used and versatile tool, and we'll use it a lot to understand a very simple process. So we'll start with a simple process, and we'll add things like capacity to it. We'll add and look at utilization and bottlenecks. But the big thing we'll add to make it really interesting is variability. As we've discussed in previous lessons, variability kills. It's the thing that really drives the system. And we can think of variability being in variability of the input, of the arrival time, or of the output. And to do this, we want to start breaking up this process into the actual internal process, but also something called a queue. And that's where the name comes for queuing theory. Because as things come in, they might wait for that processing time. And so the way things arrive, they might queue up because there might be variability in how they arrive. There might be variability in how they're processed. therefore giving variability in how things are outputted. So variability is a big driver of some of the challenges that happen to a queuing system. So what we're going to do is dive in a little deep to this because queuing theory is a very deep pool. We'll go into waist deep maybe, but we want to understand different types of queues because you can characterize them. You characterize them by how things arrive, by the rate at which things are processed, the number of servers that you have, and in this case I have one server, but you could think of going to a grocery store where you have 2 or 3 checkouts. Those are servers. And then if there's any capacity. So this is the way that we characterize a queue, and we'll look at different ways and mathematically model how the variability affects this and how it affects the throughput, the WIP, and the cycle time. We'll spend a lot of time on a very special queue called the MM1, which this means is my arrivals come exponentially, I process them exponentially, and there's one server. It's a classic queuing model, and it's kind of the basis of things. So we'll go through all this. It gets a little deep, but it's really powerful. The things I want you to remember long term, always remember Little's Law, and always remember how to characterize a queue. And we'll talk about how to measure and quantify the impact of variability. However, real life doesn't always operate like an MM1 queue. So you have things that happen weirdly. So here's my ATM machine, right? So I'll just write that it's an ATM so you know what it is. So what happens at an ATM machine? Well, can we model it as an MM1 queue? Maybe, but it's not really realistic because you can think of what happens here. I know there's a ATM machine right outside of a Kendall Square T-stop where I work. And what happens is usually if one person is coming in to use the ATM, it's because a train just came in and there's 6 other people right behind them, right? So you have all these other people coming in too. So here I've got my queue, these are my inputs, here's my process, and people want to get out, they want to get their money or they want to get their deposit done. But the point is, the arrivals always don't follow these nice distributions. They might be batched. They might come at a very different empirical distribution that we don't have a nice theoretical distribution to map. That's why we use simulation. Simulation lets us capture those systems that don't fit into these nice models. This is a great place to start. Think of it as the EOQ of queuing. You start with a simple model, see where it varies from what's actually happening, and then you might want to simulate a solution if you need to. And so to simulate it, you use something called discrete event simulation. What does this mean? Well, you can think of it as a system, and so for this, my ATM system would consist of all the people coming in, and this would be the queue, right? These people are queuing, here's my process, the ATM, and then going out. So this is my system where different entities, the people, interact with other entities, the ATM machine, and for some purpose. So within this system, you think of state variables. What's a state variable? These are, so that should be state variables. Let me just correct that really quick. Variables, there we go. All right, so what does this mean? This means I can tell the state of the system by looking at certain entities, what their variables are, such as the number of customers waiting, such as the number of open servers, right? The length of the queue, the time of the queue. These are things that describe the state of the system. And once I know the state of the system, that's how I model and simulate the environment. That's how I can measure it. So we call it discrete event simulation because we only care when an event happens. An event happens when it changes the state of the system. A new customer arrives, a customer is served, a customer leaves. So by doing this, I only have to model when the events occur. And so what we're going to do during the lesson is I'm going to give you a little bit of an overview, but then we're going to go into great detail for a specific system, which is queuing at a kiosk at an airport, where you have people coming in, and they'll wait in a queue, and then there's some kind of kiosk here that they'll serve them, get their airline tickets, and then go. And what we'll do is we'll build this system using a software package, and we'll keep adding complexity to it. And I want you to see how we can model a more realistic system step by step, but we start with this. Okay, so we're going to cover the same problem in 2 very different ways this time. We'll talk about it mathematically with a queuing model, and then we'll simulate it using discrete event simulation. All right, so do the quick questions, try the practice problems, have fun.